Okay, this is another structure we briefly mentioned, and people have flipped over their skulls and say, what's that hole? And I said, that's the carotid canal. The internal carotid artery, which is responsible for supplying blood to the front part of the brain and a few other structures along the way, comes up, right? What ultimately starts down as a common carotid artery down in the superior mediastinum, and that splits into an internal and external carotid. And then the external carotid, as the name implies, sort of stays on the outside of the skull and sends stuff in. The internal carotid comes up along the neck, goes into a hole in front of the foramen magnum, loops around, and ends up in here in the middle cranial fossa, heads forward, and then changes its mind and loops backwards. Okay, so it's traveling through this canal in the cranial base. And as it comes through, it passes over that foramen lacerum. That place, I say, it's a great big, it looks like a big place in a skull, but in fact, in a living person, it's covered with cartilage. But the carotid canal opens up in the back, in front of the foramen magnum, and then the internal carotid artery travels up and goes into the neurocranium, travels forward, and then loops back, and then sends blood into the whole front end of the brain, which we'll talk about later. Okay. There is the carotid canal. There is a little groove for it out here, which we won't pin, I promise. And then it trans up. It comes by this anterior clinoid process. The sella turcica has an anterior clinoid process up here and a posterior clinoid behind it. So the carotid moves anteriorly and then loops around and comes back to the edge of that anterior clinoid process before it gives rise to all sorts of anterior cerebral and middle cerebral arteries and little arteries to that's the orbital nerve there, goes a little artery there, and so forth, which we'll discuss later. But know roughly where the carotid artery passes. When we get to that part of the dissection, we will put pipe cleaners up it so you can see the pathway. So this is shown in on the skull. So it comes through the carotid canal over here, travels over the foramen lacerum, loops forward here into the middle parts of the middle cranial fossa, loops back under this anterior clinoid process right there on the side of the sella turcica, and then goes forward and sends arteries that way and arteries this way and arteries that way. So there's the foramen magnum. There's the internal carotid coming down there. Okay, so that's roughly where the carotid canal is. From another view, totally lateral view, coming in from here and then coming forward like that. And this is that foramen lacerum, but it's covered with cartilage. Okay, now just a brief indication of how skulls grow. Again, remember, one way of dividing the cranium up is into the neurocranium, the part that's roughly surrounding the brain, and the viscerocranium or splanchnocrinium, the stuff that's roughly surrounding the nasal cavity and the oral cavity, and obviously where all the teeth lie. Okay. Unlike the bones that you're more familiar with, your arm bones and your leg bones, which generally have, a bony part and then an epiphysis, an end with a cartilaginous plate in the middle, and they just sort of get longer and longer. Some bones in the skull actually start out having a roughly the same shape made out of cartilage, and then in the course of development and also growth, the cartilage is destroyed and replaced by bone. The cartilage doesn't change into bone, but some structures come down and eat away the little things, eat away the cartilage, and put bone down in their place. They are referred to as cartilage bones. And the formation is referred to as endochondral ossification. So, internal ossification in the cartilage. It's like I say, it's not really in the cartilage, it's a replacement of the cartilage. Other bones are not preformed in cartilage, but as fibrous connective tissue. And then this connective tissue changes itself into bone. And they're said to be membrane bones. So this fibrous connective tissue is a membrane, and it changes to bone. So that's referred to as intramembranous ossification. So within the membrane, the fibrous tissue becomes bone. So it's not a cartilage precursor. Okay, the cartilaginous part tends to be the skull base, and the membranous part is the rest of the stuff. Okay, so let's look at the cartilaginous part. Okay, here's looking at the skull from the top, the cranial base along in here, right? We're going to focus particularly on this cranial base here. Okay, so this is a very generalistic view of the base of the skull, and in very, very early development, here's your foramen magnum there. This is the otic capsule, hypophyseal fossa, and the nasal capsule. This is a very unhuman-like skull structure. And you have lots and lots of bits of cartilage throughout this cranial base. And they have different fancy names, which they're not responsible for. Okay, obviously ex-occipital is out here in the occipital region. Basi-occipital is the area between the foramen magnum and the sphenoid up here. Basi-sphenoid is this area here. And these ossification centers, these cartilaginous centers, have individual names. So there's the ethmoid region up front, followed by the sphenoid further back, the temporal region back there, and the occipital region back there. So each of these cartilaginous centers are in areas that are going to become different bones within the skull. And they have individual names. Okay, so here's the base, all this area, right, that is preformed in cartilage. Okay, and within these parts of this cartilaginous cranial base are ossification centers, seen in cross section. So that's the basi-occipital region, the basi-sphenoid region, pre-sphenoid, so this is obviously where your sphenoid bone's going to be, your mesethmoid, right, that's where your ethmoid bone's going to be, and then the basi-occipital and the supraoccipital, so this is where your occipital bone's going to be. There they are in yet another view. And as they get bigger and bigger, the bones sort of take their own shape, and many of these fuse together so that you don't see little dots. Your skull isn't made up of little dots, it's made up of more complex structured bones that started out from little cartilaginous centers that gradually grew and ossified. Okay? And where these bits have come together, they are referred to as synchondrosis. Chond refers to sort of cartilage, and a synchondrosis is where these two of these cartilaginous precursors come together. So these are specific areas that are where major ossification centers preformed in cartilage then join together in the course of cranial development. And this is when these bones get formed and actually come together. Okay, so this is your basi-occipital area, and this is going to be your sphenoid bone, obviously. And so the spheno-occipital synchondrosis between the front of the occiput, basically, and the back end of the sphenoid bone, actually only fuses together after puberty. So these are separate bony areas that only fuse fairly late in development. The sphenoid bone, before birth, has got lots and lots of different centers. It's got lots and lots of different parts, But this mid-sphenoid, this thing that's lying pretty much in the middle of the sola turcica, comes together right after birth. So this basic sphenoid cartilaginous center and this this pre-sphenoid area, they fuse up so that your sphenoid bone is one bone, and that takes place right after birth. The connection up here between what's going to be your ethmoid and the sphenoid back here takes place even later in early childhood. So these different cartilaginous area precursors form bones, but the different formations come together at very different times during the course of development. So this is a person, this takes place after puberty, and obviously the spheno-occipital synchondrosis, this is your occipital area back down here, this is sphenoid up in here. This is still not come together. This person is not reach puberty, 10 or 11 years old maybe. Okay, other bones, like I say, are formed as connective tissue, and this is conveyed directly into bone. They don't pass through a cartilaginous situation. And this just, so basically, the intramembranous, so these membrane bones, the bones forming, follow growth curves that are related to the development of nearby soft tissues. Okay, so this just shows how different parts of your body grow. You start off, lymphoid tissue rises really early, because as you're very early in child, you need to deal with all this world that you're coming in contact with. So you have lots and lots of lymphoid tissue. You have a nice big thymus gland and everything, and then that sort of fades off by the time you reach young adulthood down here. Obviously, reproductive organs are slow, and they go crazy in late teens and adolescence. That's what adolescence is all about. General growth has a slow curve until you reach adolescence. And general, muscles and bones and stuff hit what's known as an adolescent growth spurt, and the rate of growth goes very high. Brain grows a lot early, but by the time you're 10 or 12, your brain and spinal cord have pretty much got where they're going to be, and they just hang on for the rest of your lives as best they can. Okay. So here are some of these membranous bone areas. So there's a center in the parietal area, center in the frontal bone, an interparietal area back here where the parietals join the occiput. Okay, so these are, as these bones, they're not preformed in cartilage, so you don't start off with cartilaginous things there that are replaced by bone. You start off with a little bit of bones that basically spread, and they grow, and they grow. And by the time you're born, you have real bones surrounding most of your brain case, but they're not, you don't have these sutures. These sutures have not formed. So we have some baby skulls around here. Maybe we'll put one out for you to, we'll definitely put one out for you to see. And if you look at a baby skull, you've often got a right and left frontal bone. This mitopic suture doesn't really exist. There's a huge gap. The sagittal suture, these bones haven't come together. There's a huge gap there. And this coronal suture hasn't come together, so you've got this huge big area around here, which is called a fontanelle. So there are parietal bones that's formed, but they haven't grown, these individual cranial bones haven't grown together. So there's huge gaps of just connective tissue separating these individual bones that are becoming ossified. So there's a big gap here, right, where your lambdoid suture is. This is lambda. And a big one here where bregma is. There's a great big opening because you've got four bones coming together. None of them has reached full size yet, so this suture doesn't exist, this suture doesn't exist, but you've got a huge gap in there and a huge gap in there. So why do they fuse up? What's the big deal of having some gaps between your skull bones? Why do things that way? Obviously, particularly for humans, getting a baby from inside the uterus to the outside world is not an easy process. These babies get bigger and bigger, and in humans, the heads are the biggest things. If you have to squeeze these baby heads through the birth canal, getting through the bits and pieces of pelvis that are sort of getting in the way, if you can sort of squash those heads, you have a little better chance of getting through. You can still have a big brain, but you don't have to have a hard skull around it. Likewise, as your head still continues to grow, as your jaw muscles grow and other parts grow, don't make this a single bone. Keep gaps between them. It enables, the skulls to grow, but nevertheless, the sutures are sort of interactive, so they don't slip and slide. They can grow without, changing position greatly. There's a big debate over why many people retain sutures in adulthood. Why not just, you still have these interfingering things. Often they're not mobile, sometimes they are, but people debate over, particularly the ones between the temporal bones and the parietal bones. Many people argue that in fact does move when you're chewing. So that you're chewing, and a lot of that force is coming into the bottom of the temporal bone, and that there's some sort of force reduction. That you got all these chewing muscles coming off of, or the big chewing muscles coming off of the parietals, and then the jaw joints articulating with the temporal. And people have tried to sort of measure how much movement there might be between that suture between the squamosal region of the parietal, of the temporal, and the parietals above. So whether there's anything going on in sutures in adulthood it's not clear. There's nothing firm. Okay, that's the end of the lectures on skulls. So for the rest of this afternoon, God, perfectly on time. Good thought. I have a quiz for you, just to keep your minds alert. And then